Hi, all the students. Welcome to our chapter 3 on the analysis of statically determinate truss. As you may recall, we studied about the truss when we took the engine static. We use the truss in many kinds of structure. For example, the roof of a building or the bridge structure. For the roof of the building, we call it roof truss. For the bridge structure, we call it bridge truss. The pictures in this slide is the example of the bridge truss. I took this picture many years ago when I visited New York. And you also may recall when we analyze the truss is assumed to have two assumptions. One, the joint of the truss is frictionless, and second, the load applied at the joints of the truss. And you also may recall that the member of the truss can be in compression or can be in tension only. And that's kind of member called the two-force member. Okay, and then we use the method of joints to cut each joint of the truss to determine the forces in the truss member. And also we have the method of section when we cut the section of the truss, and also we use the equation of equilibrium to determine the forces in the truss member. Okay, let's see some example. We may take a look at this big stadium. If you are a football fan, you may recall that this is the Emirates Stadium. It's Arsenal Football Club Stadium. It's in London. They use the truss on the roof that span the whole stadium. So this is the quite large truss. And also in the Wembley Stadium in London again, they also use the truss, okay, spanning for the roof to cover the stadium. This is a kind of big roof truss. And this kind of roof truss is very comprehensive. In our study, we study about roof truss, but our truss is going to be more simple. And next, we go to see the bridge. This bridge is the Tokyo Gate Bridge at the Tokyo Bay. I think it's very close to Narita International Airport. So you have the picture of the airplane here. This is one of the symbols of Japan. It's across the bay, the Tokyo Bay. So every ship that's come to Tokyo will passing this bay is kind of the welcome gate for the people who come to Tokyo. And on the bottom one is the Tappan-Zee Bridge in New York. This bridge was built in 1955 and used until 2017. This bridge has very long history of 60 plus years of services. What this means is, even though these big bridges are built with the steel and they're located in the seashore area, and it can service for more than 50 years. So it's very durable bridges. It shows us that this kind of structure are very complex also. Being an engineer involved with this kind of project is an honorable. I hope you guys in the future will have this chance to do so. Okay, that's very big structure, and this structure built by using Truss. We come to our study. Okay, the chapter 3, analysis of statically determinate Truss. We have two learning objectives in this chapter. One, be able to classify various types of truss. There are at least 3 types of truss: simple truss, compound truss, and complex truss. Most of the time we work with the simple truss and compound truss. The complex truss, as the name mentioned, is so complex. Only the few structure uses. And then you should be able to investigate the truss determinacy and stability. As you may recall from the chapter 2, when we check the stability and determinacy, we compare the unknown reaction and internal forces and moment with the number of equation of equilibrium. That concept still apply here. Will be between the unknown. The unknown in the truss is going to be the reaction and the force in each member of it. So the relation is R. The force in each member is B. So the total unknown is going to be B plus R. And then compared to the number of equation of equilibrium, each joint of the truss is the pin. And when we analyze the pin, we use the concept of equilibrium of particle in chapter 3 of engine static. And you know that the equation of equilibrium of the one pin is only 2 equations, summation of x of x equal to 0 and summation of f of y equal to 0. So if you have a number of joints of 10, so you're going to have the total of 20 equation of equilibrium. So if 10 is j, so the number of equation of equilibrium is going to be 2j. So the b plus r, the unknown, will compare with the number of equation of equilibrium 2j. As you may know, if they are equal, that structure called statically determinate truss. If the unknown is larger than the number of equations, that structure called statically indeterminate truss. And if the unknown is less than the number of equations of equilibrium, the truss is unstable. Okay, that is kind of a simple concept. And next, you should understand the knowledge and be able to analyze statically determinate truss correctly. So the problem number 2 in the examination gonna ask you about the concept of stability and determinacy, and also going to ask you how to analyze the statically determinate truss. Okay, going back to in static, we have 2 methods to analyze the statically determinate truss. One is the method of joints. We cut the joints and we draw the free body diagram, and we use 2 equations of equilibrium to analyze the joints. And we cut joints by joints by joint. We will get the whole unknown forces in the member of the truss. For the method of section, which is the second method, we just cut at the point we like to find the forces in the truss member. This method again, we draw the free body diagram of the section of the truss, and then we use the equation of equilibrium. Since the section of the truss can be considered as the rigid body, so we have 3 equation of equilibrium for each section of the truss, and we can solve for 3 unknowns. Okay, you may recall what we have it before. Okay, the picture over here on this slide is the truss bridge. Is for the train that's passing through this valley. Okay, this truss bridge is over a road go to Lopburi, as Ajahn took this picture many years ago. It's a beautiful one. Okay, next. Okay, before we go further, let's talking about the homework of this chapter 3. Based on the learning objective, the homework object of chapter 3 will contain 2 parts. The first part, they're going to ask you to classify each of the following tasks as statically determinate, statically indeterminate, or unstable. So we use the unknown b plus r compared to the number of equation of equilibrium to j. We can answer this. And if the task is indeterminate, we should compute the degree of indeterminacy of the task. That is the first part. And then we have the second part on chapter 3-12, 3-14, and 3-22. These 3 problems you got to compare the result from your manual calculation with the result from the substructure program. They must be the same. If not, you got to compute by using computer again, or you got to compute by using your manual calculation again. Okay, so we have 1, 2, we didn't have 3-12. No, we don't have 3-14. We just have 3-12 and 3-22. Okay, if 2, okay, it's 2. And then we come to consider the type of tasks. The tasks are the structure that fabricated by connecting long and straight task member at the end in the triangular shape. You can recall from the previous slide, all the tasks we are considering here have triangular shape. We can not put 4 members together and form the rectangular shape. The rectangular shape is unstable. Okay, so it must be in triangular shape. And then for the loop tasks, most of the time the loop tasks, they construct the column 1, 2, 3, 4. And while constructing the column, the welder will build the task on the ground, and then they use the crane to lift up the task into the position after we finish construction the columns. So when the task lay here and another task lay over here, the worker will lay the purlin and then weld the purlin into the joints of the task. They're going to lay each purlin, and after they finish laying up the purlin and check it's strong enough, then they put the metal sheet, the loop metal sheet, onto the purlin and bolt the metal sheet into the purlin. Okay, by that way, when we use this building, the building may subject that to the wind load. The length When it's subjected to the wind load and the rain, that load gonna hit the metal sheet first, and then it's transfer the force, the loading along the length of the purlin. So the purlin is going to subjected to the uniformly distributed load along its length. And then the joints at the purlin will resist the reaction, and then the reaction at point D will transfer to the touch joints, and point B palm also transfer to the touch joint. So each purlin will transfer the force into the joints. Okay, and also the bridge truss. The bridge truss also, when they finish building all the foundation, and while building the foundation, they fabricate the truss, okay, in the area nearby, and then they use the crane to lift each truss, put the trusses into the foundation, and then they link each truss by the forebeam. Also, on the top of the truss, they use this three beam to connect the truss to each other. After that, they lay the stinger along the length of the truss, and finally, they construct the floor to the whole area of the stinger. So when the traffic come, and also the floor have the dead load, the load gonna transfer from the floor to the stinger, and the stinger gonna be subjected to the uniformly distributed load. And each stinger can assume to be as the simple beam. Okay, and then the reaction of the stinger will transfer to the forebeam. Like this point, going to have two reactions from the left and right stinger. Also this one and also this one. So the forebeam gonna subjected 3 point load onto it, and the reaction from the forebeam gonna transfer to the joints of the bridge truss. Okay, and you may see the roof truss and the bridge truss, when we build into the building and it's built into the bridge, the structure are in 3 dimensions. But luckily, we can assume and consider only one truss. We call this kind of truss to be the banana truss. The banana truss is the 2-dimensional truss in the giving plan as shown with the yellow and the green. Okay, we just consider only one of them in 2 dimensions. Like this one also, we only consider the truss this way. So the truss we are learning or considering is also the banana truss in 2 dimensions, and the member of the truss will connect each other in the triangular shape. Okay, this is one of the example of roof truss construction. You may see the truss here. Okay, and then you also see the rest of them. While building this frame of the structure, they also build the roof, and then they use the crane to lift the roof and put the roof into the structure. Okay, the assumption for truss analysis. In the ending static, you may recall back, as I mentioned before, there are two assumptions used in the analysis of Truss. One is the connection of the truss is pin. As you may see by the construction of the truss, all the member will lay in the position that the line of centroid will cut at a point. Okay, even though this kind of connection is not fully the frictionless pin, but the behavior can be proved later that is really assumed as the pin. And the second, the force must act at the joints of the truss. And you may recall, if the member have the pin end and has no forces act between that pin end, what we call this kind of structural member from the engine static, what we call? We call it two forces member. And then if it's two forces member, the force in the truss member can be compression or can be in tension. And also, if you consider this free body diagram, you can see the A is the pin and the E is the roller. By putting the force at the middle, the truss will deflect down like this. When the deflected shape of the truss is like this, the bottom member A, B, B, C, C, D, and D, E gonna be in tension. When these four member in tension, the top two for sure is going to be in compression. So this is the guideline for you to consider the truss. And then after we finish the static, we come to the mechanics of material. In the mechanics of material, when we design the truss, we will use the allowable stress. And the allowable stress is the yielding stress divided by 2. So the behavior of the truss member under the applied force is going to be linear elastic. This is the third important assumption. And one more. The deflection that I mentioned, is it can be large? No, it cannot be large if it's the bridge truss. If we have large deflection during the traffic jam, that's going to be very, very dangerous. And the people in the car may feel very uncomfortable with that deflection. So we got to control the deflection of the truss to be as small as possible. Okay? Okay. We have the total of 4 assumptions. 2 from the engineering static and another 2 from the mechanics of material. So in the theory of structure, we have 4 assumptions for truss analysis. Next slide, we're going to compare the result by the truss analysis with pin joints as the first assumption, and the truss analysis with fixed joints. Okay, the same truss, but we use the computer program to analyze it. By the force acting on the truss with the pin joints, the forces in the truss members gonna be in tension or compression, because this way the truss member are two force members. But when we change the joints of the truss to be the fixed joints, not only the axial force occur, because when it has the fixed joints, the behavior of the truss member is going to be like a frame. That means it's going to have not only the axial force, it's also going to have shear force and it's going to have bending moment. However, when you compare the axial force from the Truss analysis with pinch joints, you can see at the bottom the force is 15, 20, 20, 50. And when you do the Truss analysis with pinch joints, the axial load is going to be 14.6, 19.378, 19.378, and 14.6. That means by using the pinch joints, the obtained forces is going to be a little bit larger. The axial force is going to be a little bit larger than when you assume the fixed joint. So when you decided this left axial force will produce a little bit larger than element than the right one. And then let us consider the shear force. The shear force here is very small. It's just about 0.5. That is the maximum. And the bending moment also very small. So we can neglect the shear force and the bending moment, and we only use the axial force to analysis and design of the truss. Okay, that means our assumption is good enough to use. This slide confirms what we're talking about, the assumption of linear elastic behavior of the truss member. The stress that occur in the truss member will less than the allowable stress. So it's going to be less than the 352 divided by 2. Okay, and the last one, the deformation of the truss will be very small. And next, most of the truss that you may see, the roof truss and the bridge truss, most of the truss built by using the steel or the aluminum. For the building, most of the truss built by the structural steel. However, the truss also used in some airplane structure. For the airplane structure, we like the structure to be low weight for the airplane to fly effectively. So most of the aluminum structure is built by using the aluminum. Okay, and also this one. And next, based on the assumption again, the truss member are two force member, and that is going to be in compression or in tension. And also going back, we're talking about the truss member must be built in the triangular shape. So this truss going to call the simple truss. Okay, it cannot be in rectangular. The truss must be built in triangular shape, not rectangular shape. Okay, and this slide shows you how the truss deform under the applied force. The truss here is the cantilever truss. Okay, it have the support on the left hand side. When you put the force to the joints, by being the cantilever, it's going to be different from the previous truss that I mentioned. This time, the top member going to be in tension and the bottom members are in compression. It's the opposite of we discussed for the simple truss. So the simple truss mostly have the opposite behavior compared to the cantilever truss. Okay, the roof truss. This is the picture of the roof truss, very similar to one we have in the F4 or F5 building in the center of scientific and equipment. And you also can see the Truss here is the Pana Truss. Each Pana Truss linked by the purlin, and the purlin joins to the Truss as the joints of the Truss. Okay, and then there are metal sheet, roofing metal sheet put into the purlin, and the force or loading distribution as I mentioned before. The Truss is good to build the roof because most of the steel truss can span up to 30 meters, like the one that we have in the canteen of the building one, of the in the academic building one. The model of the truss mostly may look like this. We build a column, and then during building the column, we build the truss, and we use the crane lift the truss up. Okay, and most of the truss we have the gasket plate at the connection to make the joist strong and with stability. And then we put the purlin link between the truss, and then we put the metal sheet on the top. So the force from the metal sheet both dead load the weight of the metal sheet and the weight of the purlin, and the life load that's maybe from the wind and rain load and construction load will distribute uniformly distribute along the purlin, and it's up to the area that the purlin going to take care of. Mostly it's take care of half of this size, and the other half take care by another purlin. The same also over here. And then the force act at the joist. So on this picture you may see, since the pink area is larger than the top yellow area, and the top yellow area is larger than the bottom yellow area, so the force acting at the middle going to be the largest, and the smaller is here, and then the smallest is here. Since the roof have two sides, so there are also loadings act to the truss in this direction. And then to increase the stability of the truss, some may put the knee brace between the truss and the column. That's going to increase the stability of the structure. Okay, there are many types of roof truss, maybe Hovey truss, Pratt truss, Warren truss. So if there is not much choices to select, you may select one of these to build your roof truss. It has been shown for many years that this kind of standard truss are strong economics with some stability. Okay, this is another type of roof truss. That's for the big hall. I don't know where is this. It's supposed to be in America. And then the bridge truss. This picture of bridge truss I took it in Phetchaburi, my hometown. This bridge truss used to carry the loading of the train that's moving from Bangkok to the south and from the south to Bangkok. The span of this truss is nearly 30 meters, and the weight of the train is a lot, so this truss is quite big. Okay, and again, if we consider the model of the bridge truss, we should think about how this bridge truss construct. As I mentioned, we built the foundation for the bridge, and while building the foundation, you also fabricate the truss in the nearby area, and then use the crane to position the truss onto the foundations, and then we built the floor beam, each of them, to link the truss, and also we put this cross member to make the truss more stable. Some of the truss have lateral bracing, the X crossing. This is very important to increase the stability of the trusses. Okay, and some of the truss may also have the portal bracing, as the picture on the first slide that we have. And then they put the stinger along the length of the truss of the bridge, and then build the deck on top of the floor beam. And we should note that the diagonal member of the truss should have the angle of 45 degrees to 60 degrees, which is a good practice to make the truss strong and has stability. Okay, the force from the deck will transfer to the stinger, maybe stinger this one and also this one. So the floor beam here gonna resist the reaction from the red and for the pink loading. Okay, and the reaction from the stinger gonna apply to the floor beam. So the floor beam gonna have 1, 2, 3, 4, and 5 points. No, actually, this one's supposed to be the member of the truss. We do have 3, 1, 2, and 3 points. And then the reaction from the floor beam will transfer to the joints of the truss. And since this joint, and this joint, 3 of these joints going to receive the same kind of reaction from the floor beam, because it's going to take the same area of the deck. And you may see that the support here will subject that to the force transfer from the floor beam also, but it's going to be half of the inside floor beam. Okay, this is a general idea of this. Change to the floor, the load from the decks apply to the stinger. The reaction of the stinger apply to the floor beam, and then the reaction of the floor beam apply to the joints of the truss. Okay, this rule apply force going to have the same value, and the force at the support going to be reduced by maybe half. And there are some standard truss. For example, the patch truss on the top, the Hovey truss, the Wallen truss. These trusses are the standard truss. You may use these truss for your future work if you like. And I show you some more example of the bridge truss. That's kind of a huge structure if you may compare the truss with the boat or the house here. Okay, we're going to classify the planar truss. As I mentioned, the simple truss built by connecting straight and long member in the triangular shape. So this truss has 3 triangular shape, may call it as the simple truss. And if the simple tasks connect to each other with the joints and the member, we call this is the compound task. This is a compound task type 1. And the complex task is going to be more complex than the simple and the compound task. That's easy to see from the picture. Okay. And as I mentioned, the compound task that's built by a simple task connect at a joint and additional member, that's called compound task type 1. And if the simple task connect by the 3 task members, that's called the compound task type 2. But mostly you didn't care much about this. And type T, the compound task come from by connecting the simple task as the member of the task. This kind of type T. So normally we didn't care much about the type of compound task in our actual work, but knowing it is better if you may go to work in America or Australia in the near future. Okay, let me back here first. Part of chapter 3. We will go to the second part later for the determinacy and stability of the task.